This video 15 is titled Character Tables and the Theorems concerning character tables. Every group is associated with a device called the character table. It is so called because it primarily gives the characters of the irreducible representations of the point group. For all applications of group theory to molecular problems, only the characters are important rather than the whole set of matrices corresponding to the irreducible representations. I shall call irreducible representation as IRREP, IRREP. To illustrate the features of a character table, I have written on the board the character table of a C2V group to which water molecule belongs. Any character table has got 4 areas. The widest area is denoted as 1. Then the other area is 2, 3 and 4. In this widest area 1, you find the characters of the irreducible representations of the point group. In area 2, what you observe are the Mulliken's notations for these irreps. R.S. Mulliken has suggested symbols or notations for various irreducible representations. An account of Mulliken's notations is as follows. Any one-dimensional irrep is denoted as either A or B. It is A if it is symmetric with respect to Cn. In the case of water molecule, the Cn is the C2Z axis. Symmetric means character under that operation is +1. So you find that under C2, this is 1, this is 1, so both are A's. If it is antisymmetric with respect to Cn, antisymmetric means the character under Cn is -1. So when you find -1 under C2, the notation is B. A two-dimensional irrep is given the Mulliken notation E, and three-dimensional T, and four-dimensional G, etc. You can notice subscripts 1 and 2 attached to the one-dimensional irreps. The subscript 1 is attached if it is symmetric with respect to a C2 axis perpendicular to Cn. In the case of water molecule, there is no C2 axis perpendicular to the principal axis. So in the absence of that, symmetric with respect to sigma v xz, to the symmetric with respect to the vertical plane xz. If it is antisymmetric with respect to sigma v xz, you will put the subscript 2. You can see here it is 1, so subscript is 1. Here are 1, subscript is 1. -1, subscript is 2. For two-dimensional and three-dimensional irreps also, one can find subscripts 1 and 2 attached, but the rules are rather involved, so we will just consider it as arbitrary labels. Then if a molecule has sigma h symmetric with respect to sigma h in Mulliken's notation is denoted by a single prime, and symmetric with respect to sigma h, anti-symmetric with respect to sigma h is denoted by a double prime. Then if a molecule has center of symmetry, you will attach a subscript G if it is symmetric with respect to I, that is character under the operation I is equal to +1, then you will put G. And if it is antisymmetric with respect to inversion, you will attach the subscript U. G comes from the German word gerade and U from the German word ungerade. in this C2V group, there is no relevance for these notations. In this context, I am reminded of a UGC NET question that was asked in June 2013. The question is as follows. I'll write the full question here. Identify the Mulliken notation for the following irreducible representation. E Cn Nc2 I sigma h net June 2013. 1, 1, minus 1, minus 1, minus 1. The options given are A1U prime, A2U double prime, B2U single prime, and A2U single prime. You can see under Cn, it is 1. The characters are either 1 or minus 1. So it is a one-dimensional irrep. The notation has to be either A or B. Because it is symmetric with respect to Cn, the Mulliken notation is A. Then it has got Nc2 perpendicular to Cn, and under that we have put minus 1. So it is anti-symmetric with respect to C2 perpendicular to Cn, that is denoted by attaching the subscript 2. And because it has I and it is anti-symmetric with respect to that, it has to be uncharic. And because there is sigma h and anti-symmetric with respect to sigma h, it should be attached with a double prime. Therefore, the answer is evidently box. Area 3 always contains 6 notations. Area 3 contains 6 notations. These are x, y, z, rx, ry, and rz. X, y, z are the Cartesian coordinates, or any function or vector component or orbital described in terms of Cartesian coordinates x, y, and z. Rx, ry, rz are the rotational motion of the molecule about the indicated axis. So symmetry of this rotational movement can be obtained from the character table. In the case of C2V character table, which I rubbed off, A1, A2, B1, B2, under identity C2 sigma V dash, it is 1, 1, 1, 1. A2 is 1, 1, minus 1, minus 1. This is 1, minus 1, 1, minus 1, 1, minus 1, minus 1, 1. You will find Z here. Then this is RZ, X, Y, RY, RX. So the rotational motions, Rx has the symmetry B2, Ry has the symmetry B1, Rz has the symmetry A2, etc. That is area 3. And area 4, you will find the squares or binary products of Cartesian coordinates like x squared, y squared, z squared against the symmetry of these squares, which is A1. Then here you will find xy binary products, xy, x, z, y, z. Against their symmetry behavior, they can denote d orbitals described in terms of these squares or binary products. For example, what is the symmetry of dz squared orbital of oxygen in the water molecule? 3dz squared. Z squared is coming here, and you can say it has a symmetry A1 in water molecule. One more character table can be given here, the one for C3V group. C3V group to which ammonia molecule belongs. C3V, it has got 6 operations, but there are only 3 entries in the character table because all operations belonging to the same class have got the same character. So there is a need for only just one column for all operations which are conjugate to one another. For example, identity 2C3 and 3 sigma v. This means sigma v dash, sigma v2 dash. All these are mutually conjugate and they have the same character. So you need allot only one column or just one entry for all operations of a class. And there is a rule. A table will contain, character table will contain as many irreps as there are classes. Because there are 3 classes, there will be 3 irreducible representations. Mulliken's notations are A1, A2 and E. E is a truly 2-dimensional irreducible representation. One has to be careful to notice the difference in the meaning of E written at the top and written by the side. This E stands for identity and this E is Mulliken notation for a 2-dimensional irreducible representation. The characters are 1, 1, 1. It is totally symmetric. Any character table will have a totally symmetric irreducible representation in it. This is A2, it is 1, 1, minus 1. This is 2, minus 1, 0. And here you will write Z. This is R, Z, X, Y. A pair of basis functions are needed for a 2-dimensional irreducible representation. 2-dimensional means there should be 2 functions forming as a set of basis functions. Here it is Rx, Ry, another set. Then x squared plus y squared, z squared coming here. Here x squared minus y squared, then xy, then xz, yz. This can be the d orbitals if a demand for their symmetry behavior is needed. The binary and square functions can denote d orbitals wherever necessary. This is area 4, this is the area 3, this is the main area 1. Where characters are given, these are the Mulliken's notation. Yes. Now we can go to the theorems concerning any character table. There are 5 theorems pertaining to any character table. I shall list these one by one. Theorem 1. Sum of the squares of the dimensions of the irreps of a particular molecular point group will be equal to the order of the group. Sigma stands for sum. Then the dimension of an irreducible representation is easily picked out by looking at the characters under identity operation. Here it is 1, so it is 1-dimensional. Here it is 1, 1-dimensional. Under identity it is 2, so it is 2-dimensional. Square the dimensions and add them up. Let the dimensions be denoted by L1, L2, L3, etc. So I will write it as L1 squared plus L2 squared plus L3 squared plus etc., which can be abbreviated as sigma Li squared, which can be further denoted as sigma character under identity operation squared. This is for a general irreducible representation. It is added over all the irreps. You can easily verify this rule by looking to the C3b character table. These are the dimensions. So 1 squared plus 1 squared plus 2 squared. You get 6. 6 is the total number of operations in C3b group. The order of the group is denoted by H. This will be equal to H. Second rule is sum of the squares of the characters in any irreducible representation is also again equal to H. Sum of the squares of the characters. Character is denoted by chi. Under the operation R, you can write chi R. Any irreducible representation, let it be I. And we have to square it and add. So sum of the squares of the characters for any irreducible representation over all the operations will be equal to H. Consider A2. Character is 1, 1 minus 1. So 1 squared plus 1 squared. There are 2 operations here, so I have to multiply with 2. Then minus 1 squared, square of the character. Because there are 3 operations, we have to multiply it with 3. That has to be 6. Minus 1 on squaring becomes plus 1. So 3 plus 2 plus 1, that is 6. Here also, for the E-type irrep, 2 squared plus minus 1 squared into 2 plus 0 squared into 3. So it becomes 4 plus 2 plus 0. The order of the group. This is the symbolic way of writing the rule 2. Then rule 3. Sum of the products of characters of any 2 irreducible representations will be 0. Sum of the products of characters. So if this is character of the ith irreducible representation under the operation R, and this is the character of the jth irreducible representation under the character R, these are the products. And if these products are summed up, that will be 0. R, operations. Let us check this rule 3 by considering these two, A2 into E. 1 into 2, the characters under the corresponding operation. 1 into minus 1, because there are 2 operations, into 2 plus minus 1 into 0 into 3. Whenever 0 comes in multiplication, that term simply vanishes. So this becomes 2 minus 2 plus 0 equal to 0. You can see, check A1 and A2. 1 into 1, 1 into 1 into 2. 1 plus 2, 3. 1 into minus 1 into 3. So 3 minus 3 will be 0. Sum of the products of characters of any 2 irreducible representation, I is not equal to j. They have to be different irreducible representations, is 0. the fourth and the fifth rules are already utilized by us. The fourth rule simply says the character of all the operations belonging to a class in a representation, whether it is reducible or irreducible, are identical. That is why we have only just one entry or one column for all the operations belonging to a class, because they have identical characters. And the last one, any group contains as many irreducible representations as there are classes in it. As many irreps as there are classes in it. All these rules originate from a single important theorem concerning the elements of matrices constituting the irreducible representations. There is a single theorem concerning the elements of matrices of the irreps. This single theorem is actually part of quantum mechanics also. It is called the great orthogonality theorem, usually abbreviated as GOT. In one of my future videos, I shall illustrate in detail about GOT, and you have to know about orthogonal vectors to completely grasp the great orthogonality theorem. So at this point, I'm stopping this video. Thank you.